Hello everyone, this is the presentation of the paper Interchangeability of Fuels in Premixed Reagent Wall Burner, a CFD approach, for Brazilian Congress of Thermal Science and Engineering. My name is Rodolfo and the other authors are Layete Messias Soto and Leia Soledad dos Santos. I'd like to start the presentation answering the question, what is interchangeability? According to Natural Gas Council Interchangeability Task Group, we can define interchangeability as the ability to substitute one gaseous fuel for another in a combustion application without materially changing operational safety, efficiency, performance, or increasing air pollutant emissions. The concept of interchangeability is intensively applied in petrochemical industries where off-gases can be used as fuel instead of burning it in the flare. The goals of this work are first, determine maximum heat rate with a substitute fuel based on amount of air entrained into the burner, and second, discover burner limitations factors. A relevant chemical reaction in petrochemical industry is the cracking of naphtha into unsaturated hydrocarbons. Naphtha is fed in the coils usually centralized inside the cracking furnace, where the process temperature is controlled to about 900 Celsius degrees and the furnace temperature is about 1100 Celsius degrees. An important characteristic is the homogeneous temperature profile to avoid hot spots which can produce coke fouling inside the coils. A set of cracking furnaces may have hundreds of burners, including ground burners and wall burners. Those burners are commonly of premixed type to avail the fuel pressure coming from the off-gas process to entrainment the combustion air. This paper will treat about wall burners, so it's worth introduce the burner features. The premixed reagent wall burner have a flat flame responsible to heat furnace tiles, which will irradiate heat to the process coil. The flame begins right here in front of the tip burner. The air for combustion is provided by two manners. Primary air is a result of entrainment caused by fuel jet motion inside venturi and corresponds to the main source of combustion air. Secondary air is used to complement the primary air for combustion necessity to fine-tune flame stability. The critical pressure is the pressure that separates subsonic from sonic flow, and it usually varies from 12 to 15 psi gauge. For pressures below of critical pressure, the flow is subsonic and the burner heat rate can be represented by this equation as function of lower heating value, specific gravity, nozzle orifice area, pressure difference and discharge coefficient. Wolbe index is calculated as the ratio of higher heating value and discarded root of specific gravity. But here it's used a modified Wolbe index calculated with lower heating value because the cracking furnace does not involve water condensation on flue gas. Now it's easy to verify Wolbe index correlation with burner heat rate and associate its importance for interchangeability. Wolbe index is perhaps the most popular criteria for interchangeability and is used as a reference in standards for natural gas in many countries, like those in the table. The Wolbe index range adopted by the standards are equal or very similar to the value of 5% used as a reference for interchangeability criteria. Oxygen concentration in flue gas was adopted as 2% dry and volume basis for cracking furnace safety operation. Furnace pressure has different values as function of the row of burners and they were considered -7 mm of water column for the lowest burners row and -5 mm of water column for the highest one. The internal geometry of the mixing tube was obtained through measurements and the picture here demonstrates the slice done to separate mixing tube and tip for more accurate measurements. The validation of the model is based on experiments previously made in a combustion laboratory. CFD modeling was used for primary air, and the secondary air had a different approach using pressure drop coefficients. Looking to fuels data, in specific the molecular mass, we may associate fuel 1 to a natural gas with hydrogen content and fuel 2 to a liquefied petroleum gas. Since they are from different fuel families, we can already suspect the interchangeability even before looking for Wolbe index. The lower heating values in mass base are a little bit similar, but in volume base are very different due to molecular mass. This fact has a huge impact on Wolbe index, making the index variation greater than 35%. From this evidence, we can determine that those gases are not interchangeability by Wolf-Bendix criteria. The burner is a premixed wall radiant burner with a removable muffler in pink. The nozzle is brown, which has 3 orifices with diameter of 2.8 mm. The burner tip is yellow and in red there is the mixing tube. The 3D model does not include secondary air intake in the burner tile because it's not part of CFD. Secondary airflow is required to compute burner maximum heat rate. So to model it, we consider the dimensions of annular space between tile and mixing tube and the adjustable intake opening. The pressure drop coefficients along the path were estimated with empirical correlations from specialized literature. The table presents the measured data in the modeled values for a furnace pressure of minus 5.5 mm of water column. The maximum error was less than 5% for the condition of secondary air opening equals to 20 mm. The graph contains model data for the pressures of interest, minus 7 and minus 5 mm of water column. The previous mixing of the fuel gas with the combustion air is the result of the interaction process between fuel gas jets and entrained primary air. This momentum transfer is a function not only of physical-chemical properties of fluids, but also the geometry of the Venturi and fuel nozzle. The primary air flow is dominant in the combustion process, and a mistaken ratio of primary and secondary air can lead to flame instability, for example, flashback. Navier-Stokes and continuity equations are solved for compressible fluid, without any chemical reaction and heat exchange. Also, the ideal gas assumption was used. There were tested 4 turbulence models: standard K epsilon, RNG K epsilon, K omega, and SST K omega. The table contains are physical properties necessary for the CFD simulation, and in special, the speed of sound was used to determine the boundary conditions in the nozzle orifice. Pressure at primary air intake and furnace are independent of fuel flow, but pressure at nozzle orifice is not. So the proceeding to determine the orifice boundary condition is: first, calculate fuel density with 101 kPa and fuel manifold temperature. Then, given a mass flow, calculate speed. Finally, compare calculated speed with speed of sound at the same temperature. If the answer is no, static pressure is set to 101 kPa and speed is set to the calculated value. If the answer is yes, set speed to speed of sound and set static pressure to the value that results in the density needed to achieve the desired mass flow. This proceeding is necessary because the nozzle interior is not being modeled. The domain begins in front of nozzle orifice discharge. All the meshes tested in the CFD were hexa-dominant, and the final mesh had 900 K elements. Time and RAM memory were a limited resource, so the mesh should have the minimum elements as possible, and some simplifications further the fuel injection were done. Air intake begins in the face of muffler, and furnace mesh zone was reduced to a region really close to the burner tip, which implies a distortion of velocity profile, but we can deal with it because we are not simulating combustion. Those pictures are examples of the final mesh where regions with hot colors have smaller cells than cold colors. Boundary layer cells were refined to keep Y plus values between 30 and 300. But why those values? It's because log-law can be applied and all functions are valid in this range. Here we can take a look on the refinement necessary to describe orifice. We used wall roughness to fine-tune the model to experiments because of rust and burners wear after decades of operation. The wall function called µtk, roof wall function, changes the value of µt at the wall according to the wall roughness. This wall function is based on 2 parameters, Ks and Cs, where Ks is the sand grain roughness height and Cs is the roughness constant. Cs is similar to a shape factor, and when it is 0.5, the roughness height is constant, and when it is between 0.5 and 1, corresponds to a non-uniform roughness. A complete mathematical description can be found in OpenFlow on user guide. The final result is the increase of shear stress and pressure drop across the burner, reducing the entrainment effectiveness when compared to traditional wall function for a smooth wall. To tune the model, Cs was kept at 0.5 and Ks was varied manually till the value of 800 micrometers using the standard K-epsilon turbulence model. Comparing this value with the data of cast iron absolute roughness from the website Engineering Toolbox, we verify a good agreement. The fuel used in experiments was natural gas with no secondary air and furnace pressure at -5 mm of water column. In the first experiment, the muffler was removed and the result for primary air fuel ratio was 14.6 against 14.5 of CFD model. In the second stage, the muffler is installed and the experimental result is 14.15 against CFD's 14.3. Those values from CFD model were considered well-tuned and corresponds to the accuracy needed to go ahead with more simulations. This graph summarizes the results obtained from air fuel ratio for fuel 2. To achieve the maximum heat rate, the secondary air opening was the largest and the result for the condition of 2% oxygen in fuel gas is -5 mm of water column in the furnace and was 13.3 kg per hour, producing 145 megacalories per hour, which is around 50% of maximum heat rate declared by the manufacturer. Now we have answered our first goal. We should try to discover the reasons this result is so smaller compared to original maximum heat rate, and propose simple changes in nozzle assembly to increase the heat rate. We are not considering changing the mixing tool because the venturi is a huge and cast component, so the changes applied to it should take too much effort and could be compared to buying an entirely new burner. All the conditions were the same and the fuel rate value is kept in 12.5 kg per hour for all the changes proposed. The first attempt to increase the air entrainment was change the distance between venturi's throat and nozzle. Negative values of increment represent distance reduction. We are capable to verify that the distance showed non-representative increase in primary air entrainment. If we have reduced even more the distance, the nozzle would interfere negatively in the fluid flow inside venturi's throat, because the passage would be restricted by the presence of the nozzle body. The second attempt is the number of fuel orifices. They were changed keeping the same orifice area of the original nozzle. The greater the number of orifices, the larger the area between the fuel jet and the entrainment air. But the simulations showed no expressive impact over the primary air fuel ratio, putting away the possibility of fuel contact area for jet momentum transfer. The distance from center axis is this radius containing the orifice. This distance makes the fuel flow wider through the throat, occupying more peripheral area, but the results show practically no improvements in primary air entrainment. From the graph at right, we can verify that decreasing the orifice diameter, we expect an increase on the primary air entrainment. Then, keeping the assembly of 3 orifices, the diameters were reduced to improve primary air entrainment. Looking on simulation result, we can observe on the left side graph an increment on total air when the diameter is reduced, which was already expected, but those diameters were not enough to achieve the fuel 1 original heat rate. From the diameter of 2.8 mm to the 2 mm, the orifice area is most halved, and we could still simulate even smaller diameters to reach the desired heat rate, but it would require even higher fuel pressures, which implies restrictions outside the burner domain, for example the available fuel pressure. All the other modifications before were trying to increase momentum transfer, but this one is special because we are increasing the fuel jet momentum. In other words, we are introducing more energy to the system. Although there are more complex indexes like Weaver and AGA, the Wolbe index method proved to be sufficient to indicate interchangeability without any burner modification. The concordance of the CFD model with the experimental data and with literature reports proved to be a precision and potential model to analyze interchangeability and propose modifications to the burner original project. The attempts to increase momentum transfer did not make difference in primary air, so the transfer is not the bottleneck. But when we increase the fuel jet momentum, we have got more expressive results, which demonstrates that the geometry and high wall roofings were dissipating too much energy and restricting the air passage, impacting on a substoichiometric combustion at high fuel rates. The references used in this slide presentation are listed here. The data published in this article are only for means of illustrating the applied methods. And finally, I would like to thank you for your attention.